Hi everyone. In this video I wanted to show you a very simple but perhaps useful workflow that you can accomplish with Topologic to basically starting with perhaps a group of faces like what you see here on the left side for a building that my colleague Ahmed Al-Tahlawi gave me from TestFit. This is a TestFit model that has been converted into a BREP and brought into Blender. And the idea here is, how can we simplify some of the faces? Perhaps if you want to, let's say, laser cut them or send them for manufacturing in some way. You notice that the roof example here, the roof surfaces, which are made out of individual rectangles, end up being like this on the right. So the idea is to take those faces and then try to convert them into a wire, but then when you look at this wire again, it has a lot of redundant collinear edges, so we will also clean that up, and then at the very end we reach a very clean external boundary for this set of faces. So let's get started. I do have the whole workflow here, and I'll try to share that as well, but what I'm going to do right now is actually simply delete it and start again. So let's go ahead and remove these, and let me show you where is the starting point. So there are a series of boundary representations, or BREP files as we call them. One is called amenity, one is called common, lift, parking, stair, and unit. Those are the same names that TestFit will have for these types of cells or solids. So these are what you see here. Right, so this is a very clean model. It's all really nicely kind of put together, and we can build a cell complex out of this. It takes about currently 4 minutes for this cell complex on my computer, or it's not a very powerful, actually it's a Nook, so it's a very small computer. But for this tutorial, I don't need to create a cell complex, so I only need to get the faces. So let's go ahead and get started. So you'll notice here that what we have, if we put a stethoscope on this, that we have these clusters. So each one of those are clusters. So I'm gonna get the faces of these clusters. So that you can get that in Topologic using something called Subtopologies. So we look for Subtopologies, and we choose face, and we feed it these topologies, these 6 topologies. So now we have all these faces, and I'm gonna go ahead and flatten. Now if you want to flatten these, obviously there is list.flatten, but SphereChalk has a really nice option here where you can show the socket menu. So if you show the socket menu, you get this little pull down menu where you can say, I just want to flatten them. And you'll notice that we have 2,172 faces. All right, so these are all the faces in this building. So the question is, how do we isolate the faces that we're interested in, which are the ones at the top on the roof? Now we know 2 things. We know that these faces face forward, or face upward, excuse me. So their Z on the normal will be 1. And we know that they are at a height of 21 because every floor is, I think, 3 meters, and we have 1, 2, 3, 4, 5, 6, 7. So 7 times 3 is 21. So we can use this information to isolate them. So let's start first of all by figuring out the ones that are facing upwards. We're going to get some additional ones, but that's okay. We can filter them later on. So the first thing I'm going to do is go to face.normal at parameters. Normal at parameters. So that means give me a perpendicular vector at a certain parameter, which is in this case the centroid, which is 0.5, 0.5. And I'm also only interested in the Z component. I don't need X, Y, Z out of it. So I'm gonna just look at the Z component of it. So I feed it all these 2,172 faces, and I can get now 2,172 Z components. And as you can see here, some of them are -1, that means they're facing down. Some of them are 0, so they're facing sideways. And some of them are 1s, that means they are facing upwards. So let's go ahead and filter these faces based on what we see here. So let's go ahead and do list mask, excuse me. And it is called list mask out, this one. And it needs a data and a mask. So a mask is like, it's like putting a mask on your face, basically. It hides some things and it shows. So the way the mask is formed, it will affect what the data is. We could say that it is equal to 1, and that will be true or false. So we need a list of true and false here. If we only had 0s and 1s, maybe we could have used that. But I'm going to use a logic node. And let's just call it logic functions. And I'm going to choose equal, which means is it equal to? And I'm only interested in the things that are equal to 1. So I will feed it this list of 2,172 values, and I'm going to check what I'm getting as a gate. Now it tells me that it's out of range, and the reason is that these are not wrapped. They have one square bracket rather than two, and this is a quirk of Spurchock. They expect things to be doubly wrapped. Topologic kind of doesn't follow that convention. I prefer a simplified version where everything is single wrapped. But if it doesn't work, try always to like wrap it, choose wrap here, and you'll notice that now it has worked. So whatever is not 1 will be false, and whatever is 1 will be true. So we can use this mask here on this node, and we feed it those faces, and it will match then whatever is true, and it will give you only the ones that are true, and it will omit the ones that are false. So here under data true, it will give you the ones that are true, that are actually facing upwards. So let's visualize that. I'm going to make a copy of this. This is just topology.geometry and then a viewer drawer, so that a menu. And I'm going to hide this building. So with this little eye here, you can hide it. And we take the data that is true and feed it here. And as you can see, it's all the horizontal slabs, all the slabs that are facing upwards. All right, so we got those, but now we want only the top one. And obviously the top one has a Z of 21. So we can look at the centroid of each one of those, or the center of mass of each one of those faces, and filter according to that. So we start from the data true. So now we have reduced it to 347 faces. We start from here and we repeat exactly the same thing here to create a new mask and filter it some more. So again, I'm going to look for the logic function, and it should be perhaps greater than. We'll get to that in a little bit. But how do I get the centroid? So we do topology.centroid. So centroid is the average of the vertices of a shape. It just concentrates on the vertices and gives you the center of them. But center of mass is a little bit more sophisticated. It really shows almost like the center of gravity of a shape. So it's completely up to you. Centroid is usually a much simpler calculation. So if you don't need anything more sophisticated, centroid is fine. So I'm going to get the centroids of these. Let me just show you what these look like. These will be vertices, topologic vertices. Here we are. So now what we need is their Z. So we can choose vertex.coordinates. And again, same before as the normal, you can choose whether you want all 3 coordinates, or are you interested in a pair of them or just one of them. We're interested only in the Z. So we, do the Z on it, and let's look at what these look like. So again, these are numbers, 7, 3.5, 10.5, etc., etc. Not sure why I have 10.5s, maybe something in between. I'm not absolutely sure, but the highest one is 21. I mean, we could look at the maximum and say, okay, we're going to use the maximum, which is the topmost. That would be another way of doing it. But since we know it's 21, I'm going to do a logic function where, you know, it is greater than 20. Anything greater than 20, just go ahead and give that to me. So I'm going to say anything that is greater than and greater than 20. And I think I need to wrap these as well and feed that in. And now I should get a list of true and false. You can see them here. And I can use that as a new mask to filter those 347 faces. So again, I do list mask out, and I give it those 347 faces, and I give it the mask. And now I should have only the top faces that you see here at the top level. So again, I copy these to be able to visualize. And let me take the data that is true, and let me hide this one, and you'll notice what is left is the top. These are the top ones. Here we are. Great. So we now isolated these top faces. So the next issue is that these are actually individual faces. How many are they? There are 89, as you can see here, 89 individual faces. So we need to get the outer boundary. So one way in the new release of Topologic to do this is to create a shell by these faces and get the external boundary of that shell. So I'm going to go ahead and say shell by faces. So shell is exactly as it sounds. It's basically a group of faces that are interconnected. They share edges. And you create a shell. It can be open or closed, doesn't matter, almost like a cardboard box, but all the faces need to be touching. So I give it those 89 faces, and let's see what we get. Again, I put a stethoscope on it just to kind of make sure that I got myself a shell object, which is correct. All right, so now I can say shell.external boundary. So here's the external boundary, and let's go ahead and visualize that. So let me copy this again, like this, copy paste, Control V, Control C, Control V, save it. Let's go ahead and hide this, and you'll notice now I have the external boundary, and this one is a wire. If you wanted to see, I will deviate just a little bit to show you shell.internal boundaries. That will give you a list of edges. So let's go ahead and exercise that a little bit. Just a little bit of a detour here. And these are the internal boundaries, all the internal edges. All right, so we're back to the external boundary. So the next step is to remove all these vertices and just leave the main ones where, you know, it changes direction, but all these collinear edges need to be removed. So again, we have something called topology.remove collinear edges, and this works on shells or faces, anything that has edges that may be collinear. It will clean those up for you. So in this case, I am taking in the topology. It has a couple of parameters, just a regular tolerance, you know, this is needed for general kind of rounding errors, and then an angle tolerance, which is important. This is in degrees, so 0.1 is enough. It should catch everything like here, but if you find that it is not catching one of them, just increase the tolerance a little bit. Obviously these angles here are 90 degrees, so they're way above 0.1. All right, so this should have been now a clean wire. So let's go ahead and visualize that. Again, another copy of this. And we do that here, and we hide this one. And here we are. So this, let me just hide it to show that this is the one. This is now the cleaned up wire. It has only these, you know, vertices. And then you can make a face out of it if you want. So I can say, for example, face by wire. If you want it to be an actual face, and let's reuse the same node to visualize it, and there it is. That's it. I hope you enjoyed it. Thank you.